Dr. Abhishek Joshi, and in this video lecture I am going to discuss about QPSK and M-array schemes. So what is QPSK? Let's discuss. So QPSK stands for Quadrature Phase Shift Scheme. Quadrature means in a Cartesian it is this portion of the xy plane. Okay, if this is x, this is y. So this is the first quadrature when you are talking about the Cartesian coordinate system. So in QPSK, this quadrature stands for the single phase is identified within one quadrature. So this means this phase will be 90 degrees. So in quadrature PSK, each and every symbol are separated by 90 degrees. So this is known as the quadrature phase shift keying. Now how we can generate this quadrature phase shift keying and how we can detect it at the receiver side, we are going to discuss in this lecture. Then it will be further discussed that what is M-array communication and how we can generate M-array communication with a smaller bandwidth because channel is band limited. So the spatial PSK signaling where number of symbols are M equals to 4 is an extensively popular powerful digital modulation format. So in this a summation of two binary PSK. So this is the important thing that we are using the two binary signals that are in phase and quadrature phase. So we have in phase carrier and a quadrature phase carrier in case of a QPSK. So we can consider that QPSK is a combination of PSK with one carrier FC1 and PSK with another carrier that is FC2. Okay, so we have two carrier which is in phase and quadrature phase. That is, you can say that in phase and quadrature phase are separated by 90 degrees. So phase difference between the in phase and the quadrature phase is 90 degrees. So for this reason it is known as the quadrature phase shift keying or QPSK. So we can transmit and receive both these signals on the same channel, thus doubling the transmission rate. So it doubles the transmission rate, so bandwidth occupied will be less because we are transmitting two symbols in the same bit interval. So in QPSK, that is quadrature phase shift keying, as with the binary PSK, information carried by the transmitted signal is contained in the phase. So information is holded by the phase. So in particular, the phase of the carrier takes on one of the four equally spaced values, that is pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. So we are having four different phases that is holding four different symbols. So symbols, so four levels. If you are considering four levels 1, 2, 3, 4, or it may be 0, 1, 2, 3. So we can classify 0 as, so 0 can be written as 0, 0, 1 can be written as 0, 1, 2 can be written as in binary format, it is 1, 0, and 3 can be written as 1, 1. So we can use these symbols to classify the symbols or classify the different phase. So all these symbols, that is 0, 0, 0, 1, 1, 0 and 1, 1 will be separated out with phase, that is pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. So for this set of values, the transmitted signal can be defined as, so we can define the transmitted signal that is SIT, that is signal in the time domain, that is equals to under root 2e by t cos of 2 pi fct and 2i minus 1 pi by 4 ranging from 0 to t and 0 for elsewhere. So where I is equals to 1, 2, 3, 4. So we have the integer I which is holding four different phases. So phase is defined here. So that is 2i minus 1. So if you put I equals to 1, so it will be 2 minus 1. 2 minus 1 will be 1 and pi by 4. So first phase will be pi by 4. Next phase, if you are putting I equals to 2, so it will be 4 minus 1, that is 3 pi by 4. Third phase, if you are putting I equals to 3 in this, So it will be 2 into 3, that is 6, minus 1, that is 5, that is 5 pi by 4. Similarly, if you're putting 4, so 2 into 4, that will be 8, 8 minus 1 will be 7, and 7 pi by 4. So there are 4 different phases for the integer values 1, 2, 3, 4 when you're substituting in this. Now how we are writing this amplitude? So amplitude, I've already explained in the previous lecture this is the nothing but the relation between the energy and the amplitude when you're considering a cos of omega ct as a carrier. So we are having 4 different symbols which can be written as. So for dibits, when we are talking about dibits, so we are classifying 4 different levels, that is 1 1, 0 1, 0 0, and 1 0. So 4 different levels are having 4 different phases. So we can write it as, that is a cos of 2 pi fct plus pi by 4, a cos of 2 pi fct plus 3 pi by 4, a cos of 2 pi fct 3 pi by 4, and a cos of 2 pi fct minus pi by 4. So here you can write minus 3 pi by 4 as well. So each values of the phase corresponds to the unique dibit. So we have the unique dibit, okay, means 2 bits, the combination of 2 bits are known as a dibit. So it may be 0 0, 0 1, 1 0, and 1 1. So these are the dibits which we are modulating with the help of the QPSK. So set of phase values to represent the gray encoded set. So gray encoded set for 0 0, 0 1, 1 0 can be, this means each and every dibit are separated by a single bit, or you can say the distance between the two symbols in a 1 bit. So we have 1 0, 0 0. So here the difference between these two dibits are 1 0 and 0 0, only a 1 bit difference. Here 0 0 and 0 1 is separated by 1 bit. Here 0 1 and 1 1 is separated by only 1 bit. This. So as you can see, all these gray encoded bits are separated by only 1 bit, with only a single bit is changed from one dibit to the next. So this I have explained to you. So to redefine the transmitted signal, that is SIT, for the interval ranging from 0 to t in the equivalent form, so it can be written as, that is SIT is equals to, that is under root 2 e by t, that is from the same equation which we have written earlier, that is cos of 2i minus 1 pi by 4 to define 4 different phases, cos of 2 pi fct for the carrier, minus under root 2e by t sine of 2i minus 1 pi by 4 and sine of 2 pi fct. So here this thing we have to analyze that these two are different functions, that is cos and the sine function. And we know that when we have the cos function and sine function, these are separated by 90 degrees or pi by 2, or you can say 90 degrees. So cos and the sine functions are separated by 90 degrees. So we can use the cos function and the sine function to define the in phase and quadrature phase signals. So in phase and the quadrature phase signals can be defined. Now how we can generate the QPSK signal? So this is the diagram which explains how it is generated. So we have the binary input. So here you can say we have the binary input 0 1 0 like this. So sequence inputs are given to the 2-bit serial to parallel converter. Now we are converting these serial bits to the parallel bits. So 2-bit means 2 bits are transmitted at the same time. Okay. So when 2 bits are transmitted, so 2-bit serial to parallel converter, so 2 bit will be transmitted. Here 2 bits will be transmitted. Now we will be separating out the odd and the even bit. So first 2 bit, so these odd bits are separated and this will be given to this, and for the down network it is given to the even bit. So now the even bit are multiplied by the carrier function, that is a cos, and the odd bit will be multiplied by the sine function. So we are using in case of offset QPSK, this additional element will be used, that is a delay operator. So we have the in phase signal, that is I of t, and the quadrature phase signal, that is represented by Q of t, and we have the bits, that is an plus minus 1 and bn plus minus 1, that these are the datas which we are getting from 2-bit serial to parallel converter. So the bit rate is halved. here you can see that is R by 2 and R by 2. So we can write, and this is the carrier oscillator which is generating the carrier frequency, that is the in phase, and the auto or the quadrature phase signal, that is cos and the sine function, and then it is multiplied. So we are using a product modulator to multiply these two signals, and the summation will be done here, and the summed up signal is known as QPSK signal. So QPSK signals are transmitted from this point. So QPSK, we can write the mathematical equation of the QPSK as the signal, that is ST, that is 1 by under root 2 I of t cos of 2 pi fct minus 1 by 2 qt sine of 2 pi fct. So in case of offset QPSK, so this is known as a offset QPSK, quadrature phase shift keying. So in case of offset QPSK, we can write this equation as, that is S of t, that is equals to 1 by under root 2 it, that is an in phase signal, cos 2 pi fct minus 1 by under root 2 q of t minus tb sine of 2 pi fct, that is the quadrature phase signal. So there are two orthogonal basis functions for this. We have phi 1 and phi 2t. So there are two orthonormal basis functions, that is phi 1 and phi 2, and this SIT, especially when we are talking about the two orthonormal functions. So how to define these functions we have discussed in case of BPSK and ASK as well. So we can write directly these functions as the two different symbols, that is having phi 1, that is phi 1t is equals to under root 2 by t cos of 2 pi fct ranging from 0 to t, and phi 2 t, that is equals to under root 2 by t sine of 2 pi fct ranging from 0 to t. So how we can define these diabits according to the symbols? So this table shows how it is defined. So signal space characterization of QPSK, here we have the gray encoded input diabits. So here we have the 10, 00, 01 and 11. So these are the 4 diabits. For 4 diabits we are having 4 different phases. So 10 we are having pi by 4, 00 is having 3 pi by 4, 01 is having 5 pi by 4, and 11 is having 7 pi by 4. So accordingly we are having the message points or the symbols given by, that is pi by 4 can be written as plus e under root e by 2 and minus under root e by 2. Here 3 pi by 4 is written as minus under root e by 2 and minus e by 2. Only symbols are changing. So these symbols are nothing but, you can say, when you are talking about a Cartesian coordinate system, if we are having this phi 1 and this is phi 2, so these are nothing but denoting different sample points or message points. So plus minus. So plus minus stands for, here we have this plus, this phi 1 is plus and phi 2 is negative. So here we have this point. Okay, when you're talking this. Next point is minus minus. So next point will be here. Okay, so next point will be here. First point this here. So this is plus and minus. Here we have minus minus. Next is minus and plus. So minus and plus will be here in the second quadrant of this Cartesian coordinate, and then we have the plus plus. So plus plus will be here. So accordingly we have classified the 4 symbol points as, if you are talking about 10, so it will be 10 here, this will be 00, this will be 01 and this will be 11. So accordingly we are having the 4 message points when you are talking about the signal space diagram. So the same we have done here. So it is showing the 4 message points as given by, so we have the message point, that is here we have even these message points can be rotated in a signal space diagram. So here we have on the x-axis we have the phi 1, and second basis function is phi 2 here, and the 4 message points are m equals to 1. So we are writing it here 10. This is region z1, this is the region z2, or this is the second quadrant of the Cartesian coordinates, this is the third region, and this is the region 4. So we are having 4 different regions and 4 message points, that is m1 or s1. So here this is m1. So 00 we have m2, and we have here 01, that is the third message point m3, and the fourth message point, that is 11, that is m4. So we have classified 4 message points with the 4 symbols or the 4 phases, different phases. So we can write in terms of the power. The same mathematics we can apply to write the equation in terms of the power, that is in the voltage, the signals we are representing in terms of the time voltage, that is Vt is equals to under root of 2 Ps cos of omega naught plus 2 amp plus 1 pi by 4, where the value of amp is varying from 0 to 3, that is 0, 1, 2, 3. So these signals were then represented in terms of 2 orthonormal basis signals, that is U1t and U2t. So same equations we are writing in terms of the basis function and the power. So whatever we had written earlier, so same is written in terms of U1, V1, or you can say the power and the voltages. So here we have, that is U1 under root 2 by t cos of omega naught t, Ut equals to under root 2 by t sine of omega naught t. So we can write the final expression of voltage, that is under root Pst cos of 2 amp plus 1 pi by 4 under root, that is the cos function, and this one is the sine function, and these are the representation of the in phase and the quadrature phase signal. So this is I and this is Q. So we have the in phase signal and the quadrature phase signals, and these signals are nothing but the QPSK signals. So how we are separating out the even and the odd bits? So QPSK signals, that is VMT in equation, can be put in the form, that is the even bits can be represented as under root cos of 2 amp plus 1 pi by 4, and the odd bits can be written as minus of under root 2 sine of 2 amp plus 1 pi by 4. So here we have this term in terms of the voltage, that is under root EB, that is the bit energy, EB is the bit energy, and BE, that is the even bits, multiplied by U1t minus under root EB, B0t, UT t. And the time is given by the twice of the bit duration. The twice of the bit duration means here the bit rate is decreased when you are talking about bit rate, because bit rate is inversely proportional to the bit duration. So when we are saying that the bit duration is twice, the duration of the bit is twice, this means the bit rate will be halved. So signal space, so same we have represented. So odd and the in terms of the odd and the even bits. So here we have, that is odd bit is -1, even bit is +1. So these are the, you can write 0, 1. This is a symbol 0, 0. This is a symbol 1, 0, and this is a symbol 1, 1. So these can be switched. So this, even we can put, we can shift this symbol here. We can shift this symbol here. We can shift this symbol here, and shift. Even these symbols can be shifted as shown in the arrows also. So that is the advantage of using these QPSK modulated signal. The symbols can be shifted, or there may be an offset in the symbols. So the 4 message point is associated vector is given by, that is SI, that is equals to, that is the in phase signal and the quadrature phase signal, that is under root of cos 2i minus 1 pi by 4 minus under root E sine of 2i minus 1 pi by 4, where value of I ranging from 1 to 4 for representing 4 different message points. So these are the timing waveforms to represent the diabits. So here you can see the waveforms for 4 different combinations. So for 0, 1, 1, 0, 1, 0 and 0, 0, these diabits are representing the odd and the even sequence. So if you are talking about the odd number sequence, that is 0, so we can see that it is minus pi by 2, that is 90 degree. Here this is given by, so this is minus pi by 2, this is plus pi by 2, so again this one is plus pi by 2. So you can see that first we have separated out the odd bits and the even bits in a diabit. So when we are talking about the next bit, that is 1, so 1 we are having, it is starting from 0, so it is 0 degree. Here we have 0, so it is 180 degree. So this is the 1 PSK. So this is the PSK for the odd bit, odd PSK, odd bit PSK, and this is showing the even bit PSK. But this is with sine, even bit are multiplied with the sine of, or you can say sine carrier, and the odd bit is multiplied by the cos carrier. Okay, 2 pi fct we can write, and the addition of these two is nothing but a QPSK signal. So addition of these two signals are QPSK signal which is transmitted. So we have S of t that is given by this QPSK waveform. So this is nothing but a QPSK waveform which is transmitted or modulated waveform. So this diagram shows the input binary sequence, odd number bit of the input sequence, and its associated binary wave, that is PSK wave, that is even bit is also represented here, even bit number of the input sequence and associated PSK, and the final is the QPSK waveform. So same we can understand with the waveforms as, so for QPSK we are having 4 symbols, that is 1 1, 0 1, 0 0 and 1 0. So 4 symbols are, for example here we have 1 1, so 1 1 is represented by the phase pi by 4, 0 1 is represented by the phase 3 pi by 4, 0 0 is represented by minus 3 pi by 4, and 1 0 is represented by minus pi by 4. So here we have the bit sequence for the 10 time instance. So 1 2 3 4 5 6 7 8 9 10. Now we have to understand how this is working. So here we are separating out the odd and the even bits. So here we have the odd bit which is this one, 1 3 5 7 9. So 1 3 5 7 9 are the in phase bits. So we are writing as I. Okay, and the even number bits are 2 4 6 8 10. So these are the even number bits. So we are representing it by the quadrature phase bits, or you can say even bits, Q. So I'm writing Q for the even number. So where we have the in phase, or you can say the odd bits. So odd bits, so first I'm defining the sequence. So sequence is 1 0 1 1 0 0 0 1 1 and 1. So these are the bit sequence, or you can say the input signal. Now we will separate out the in phase signal and the quadrature phase signal, which is repeated twice. Okay, so here you can see in phase signal is 1 here. So 1 will be repeated twice for the 2 bit duration. So 1 we have writing double 1. So here we have single 1, or here we have the first one which is double. Now the third, now we have to see the third bit. So third bit is 1, again 1. So we have to write in form of a double bits. Now next bit is minus 1. So minus 1. So again we have to write minus 1, minus 1. Now seventh bit is minus 1. So here it is minus 1. Now the ninth bit is 1. So double we have to write 1 1. So same procedure we have to follow for the, so this is the procedure for the in phase, or you can say the odd bit. So same procedure we follow for the even bit. So first even bit, or you can say the quadrature phase bits. So second bit is minus 1. So double we have to write minus 1 and minus 1. Now the fourth bit is 1. So what, double. Sixth bit is minus 1. So minus 1, minus 1. Eighth bit is 1. So 1 1. And 10th bit is 1. So 1 1. Now we have to see the combination. So according to the combination, we have to write the phases. Now we have 1 0. So if we have 1 0, then which phase we have to follow? It is minus pi by 4. So these are the combination we have to see. So this is 1 0 means minus pi by 4, 1 1. So 1 1 means plus pi by 4. So phase difference will be pi by 4. Now next is, here we can see 0 0. So for 0 0 it is given by minus 3 pi by 4. Next bit, that is 0 1. 0 1 is given by 3 pi by 4, and 1 1 is given by pi by 4. So these are the phases for representing the die bits. Okay. Now this will be transmitted, and these corresponding phases of the output signal are written here in this form, which is transmitted. So block diagram of the transmitter, here we have the binary data sequence, which is first converted to the polar, that is 0 1 in this form is transmitted. Now these zeros and ones are converted with the help of the polar. Now these zeros and 1 we are converting in polar, that is 0 is represented by -1 and 1 is represented by +1. So in terms of the polarity plus minus 1 it is converted and then it is given to the demultiplexer, which is separating out the odd and the even bits. So once we have separated out the odd and the even bit, it is multiplied with the corresponding signal. So odd bits are multiplied by the cos function and even bits are multiplied by the sine function. So odd bits, these are the odd bit and these are the even bit. Now the odd bits and even bits are multiplied by the corresponding carrier and then these two signals are summed up and transmitted. So this is nothing but a QPSK modulator. So this is how we are defining. Now for offset QPSK we have one additional block, that is the D flip-flop and for the odd and the even bit. So here we have the bit sequence. Now we are separating out the bit sequence with the help of the toggle flip-flop, and these toggle flip-flops are given to the odd and the even bits. Okay, odd and the even D flip-flop, and these are multiplied with their corresponding sine and the cos functions, and finally these even bit and the odd bits are added and transmitted. So this is the explanation of the timing waveforms and how is it done. So here we have the clock. So this is a clock signal. Now here we have the odd clock. Odd clock is separating out for the double bit duration. Here we can see these are the odd block, and the inverted version, inversion, or you can say the inverted is the even clock. So inverted one is the even clock. Now this odd and the even clock are separating out the bits. So here we can see these are the bits, that is 00, 10, 111, 00, 10, 1, 000, 11. So this is the bit sequence which is now separated out in form of the odd and the even bit. So first bit is 0. So first see 1, 3, 5, 7, 9, 11, 13, 15 and 17. These are the odd bits. So first bit is 0. So 0 will be written for the double bit duration. So it is 0, 0. Next bit is 1. So for the double bit duration it is 1. Fifth bit is 1. For the double bit it is 1. Seventh bit is 1. So for the double bit it is 1. Now next is ninth. Ninth is 0, 0. Double bit 0. Next is 11. So 0, 0, 0. Next is 13. That is 0, 0. Next is 15, 00. 17th is the 1. So here these are the odd bits represented by V0 T. Next is the even bit. So these are the odd bits. So first we have separated out the odd bits. Now the even bits. So even bits we are separating. So we have 0. So 0 for double bit. Fourth is 0, double 0. Sixth is 1, double bit duration. Eighth is 0, double bit duration. 10th is 1, double bit duration. 12th is 1, double bit duration. 14 is 0, double bit duration. 16th is 1. So these are the even bits. So first we have separated out the odd bits and the even bits. Then according to the die bits, we will classify the phases. Now the block diagram of the receiver, whatever we have modulated, so same we have to demodulate it and we have to separate out the die bits. So these are the received signal that is given by xt, and we are multiplying these received signal with the same basis function, or you can say the carrier signal, that is phi 1t and phi 2t respectively. Then it is passed to the integrator, or we can call it as a low pass filter, because low pass filter is, the integrator works as a low pass filter. So this is also a low pass filter. So once we have multiplied these signals, we are getting the square signals, and because if we have a cos of omega ct, again when you are multiplying with a cos of omega ct, we are getting a square cos square omega ct. So we are having, if or using the trigonometric identity, if we convert it, we are getting 1 plus cos 2 omega ct by 2. So means double the frequency we will get, or double the angular frequency we will get. This means if we are passing through the low pass filter, what we will get? We will get the DC component, that is a square, or you can say if it is a polar signal, it is plus minus a square by 2. So when you are passing through the low pass filter, the output will be a plus minus a square by 2. and then we will take the decision whether the value is greater than 0 or less than 0. If the value is greater than 0, then we will call it as 1. If value is less than 0, we'll call it as 0. So here we are using the decision device, then we are again multiplexing it so that these bits are converted into from parallel to serial. So this is nothing but a multiplexer is nothing but a parallel to serial converter. So we are using the multiplexer here. Now in case of how this is feasible, or how in mathematics how we can understand. So we can understand it as, that is, we have the signal that is under root ps b naught t sine of omega naught t and plus under root ps pe cos of omega naught t. So we are raising the power to the fourth power, as we have discussed that we are using the trigonometric identity. Then we are passing through the band pass filter with a center frequency 4 f naught and dividing the frequency by 4. Okay, then we are separating out the in phase and quadrature phase signals, that is cos, and the sine phase signals, that is cos of omega naught t and sine of omega naught t. Then we are multiplying these two carriers with the corresponding bits. So corresponding bits we are getting, or you can say the received bits we are getting at the receiver side, and these are multiplied. Okay, and after the multiplication we are passing through the low pass filter. So these are the low pass filter LPF. So after passing through the low pass filter we are getting, that is that we are explained that plus minus a square by 2. So we are getting only the DC component, remaining are filtered out, and with the help of this 2:1 mux, and you can say with the help of the latch, we can convert the parallel, these odd and the even bits, or you can say parallel bits, to the serial bits. So output will be the recovered data, that is BT, or the message which we have transmitted from the transmitter. So these are the signal space representation of the QPSK and offset QPSK, where we have the 4 message points M1, M2, M3, M4, and these message points can be interchanged, or these positions can be interchanged. So same we can see in case of offset QPSK, that how these bits can be interchanged. So here we have message points M1, M2, M3 and M4. So GT, the power spectral density of QPSK, we can compare the QPSK power spectral density with the MSK. That is, we are having the higher power at the DC. So higher power at the DC. In case of MSK, it is less power spectral density, and the mathematics can be written as, the power spectral density can be written as twice of E sinc square TF, or it can be written as 4 times of the bit energy sinc square TF. Now in case of offset QPSK, the carrier phase changes by plus minus 180 degrees whenever there is a in phase and quadrature phase components of the QPSK signal changes sign. So another is that when the carrier phase is plus minus 90 degrees whenever in phase and out of phase, or you can say quadrature phase signal sign changes. And the third is the observation we can make, that the carrier phase is unchanged when neither the in phase component nor the quadrature phase component changes sign. So this I've already explained according to the observations, that the 4 message points are separated by 90 degrees. Here we can see all these message points are separated by 90 degrees. Similarly, in case of offset QPSK, all these message points are separated by 90 degrees or quadrature phase. So the basis functions for QPSK can be written as under root 2 by t cos of 2 pi fct, under root 2 by t sine of epsilon t for the duration 0 to t and t by 2 to 3t by t. So here I am going to stop this lecture. Thank you.